Hi, welcome to the video on when an alternating current passes through RC and RLC circuit analysis. So first let us take up when an AC is passed through parameters having RC and how do we analyze the circuit RC circuit. So this is an RC circuit where we have a capacitor and resistor connected in series and a voltage applied across it. So when a voltage is applied across it, the current I flows through R and C. So the current I is same which is flowing through R and C. So let us analyze the circuit. So this is R and this is C. So I apply a alternating voltage across this circuit. So let me apply the RMS voltage V and the current I flows here. And the voltage across this R is VR. Let us say the voltage drop across this is VR and across this is VC. So for this, let us draw the vector diagram to analyze the circuit. So we know that when in a pure C circuit, we have the phasor diagram for pure C and pure R. So for pure R, if this is the current I flowing, the voltage is in phase in case of pure R, correct? So now in case of pure C, we have current leads the voltage by 90 degrees. So if you observe, this is anti-clockwise. So current is leading the voltage by 90 degree. So now combining these two, we need to draw the phasor diagram for a series RC circuit. So here I will take the current as a reference because I is same for both resistance and capacitance. So taking the common of I here, okay, so VR is now in phase with I and VC is now lagging I by 90 degree, correct? So according to this too, I'm just using the same thing here. So now, so this total voltage now is your V. So the phase difference between V and I is phi. So it is lagging. So V is lagging I by an angle phi. So because since it is capacitive, so I is always leading here. So then we can write VR is equal to, I into R. VC is equal to, can be written as I into XC. So V is the vector sum of VR plus VC. Correct. V is the vector sum of VR plus VC. Now, if you take a impedance triangle, so I can draw this as R and this as XC and this as Z. So when you take an impedance triangle and this as phi, okay. So when you take an impedance triangle, Z is equal to square root of R square plus XC square. And also from this triangle we can write phi is equal to tan inverse of XC by R. Correct, because tan phi is equal to what you have the formula, tan phi is equal to opposite side divided by adjacent side. So if you take this formula into consideration and take tan inverse to the right side, so phi is tan inverse of XC by R. So now let us derive the instantaneous power now for this particular RC circuit. So the instantaneous power is given by P is equal to V into I. So when you substitute, so we know V is equal to Vm sine omega t into Im sine of omega t plus 5. Capacitive, this current is always leading the voltage by an angle phi. Correct. So when you multiply these two, Vm, Im, you can take it as common. Vm, Im, okay, into, this can be written as sine omega t into sine of omega t plus phi. So this is in the form of sin x into sin y, correct? Earlier also we have discussed this formula, sin x into sin y. So we can write sin x into sin y as formula as sin x into sin y as half of cos of x minus y, okay, minus cos of x plus y. So when you use this formula to this, so we get here P is equal to half of Vm Im cos phi, okay, cos phi minus half of Vm Im cos of 2 omega t plus phi, okay. So when you use this formula, you tend to get this here. Now the second term here, this term, okay, is double the frequency, right? Cos 2 omega t. So we have already defined this. The second term in the above equation for P is periodically varying quantity whose frequency is 2 times the frequency of the applied voltage and whose average value is 0. Hence, it does not contribute to the average value of power consumed by the circuit. So this second term goes to 0. So P is equal to half Vm Im. So if I want to write this in the RMS form, this can be written as Vm by root 2 into Im by root 2 into cos phi. So we have here cos phi, correct. So Vm by root 2 and Im by root 2 can be written as P is equal to Vi cos phi. So ultimately the power in the circuit, the average power in RC circuit, we have P is equal to Vi cos phi. So looking at this, we can draw the waveform for this particular RC circuit. So the waveform goes like this. So if you take this omega t, okay, as the time axis here, and let me draw the voltage first, okay, this is V. Now we know RC capacitive circuit, we have I leads the current by 90 degrees. So let me start, let's leading now exactly at 90 degree here. So this is pi, so this is pi by 2. So when you take this, so this will be your I. So now multiplying P is equal to Vi. So when you multiply P is equal to Vi, both the waveforms, if you observe here, you have a current here. So the power starts from here. Because I reaches 0, P also should go to 0. So the negative lobe starts here. So this can be the positive lobe and this can be the negative lobe. So looking at this, the power and the voltage and current waveforms can be drawn. So this is power. So with this, we can proceed with the next analysis of the circuit, RLC circuit. So in this, R, C and L are connected in series, where an alternating voltage is applied across this and the current I flows in this circuit. Here we need to discuss on 3 cases. That is, when you take R, L, C and a current voltage supplied across this V, R, L, C. Correct. So now there are two conditions here. Either we know XL is equal to 2 pi FL. When you write an impedance, XC is equal to 1 by 2 pi FC. Correct. So where Z will be here, Z is equal to R plus J XL minus XC. It can be of this form, or otherwise, let me take up this way. Let me take up this way. Now we can say XL can be greater than XC, or XC can be greater than XL. Okay, or it can be XC is equal to XL. So three condition we need to deal. So this is second and this will be third. So three conditions. So when you take XL greater than XC, so in that case we know so first case we can take XL greater than XC. In that case, let me draw the phasor. So let me write this as VR and this as VL and this as VC. So when you draw the phasor and when I apply the voltage, the current I flows here. So let me take a reference now, current as reference, because all the three parameters current are same. So when you take a reference I, okay. Now observe, this is VR. So always in phase with the current. Now VL, the current lags the voltage by 90 degree. If I say XL greater than XC, let me draw the magnitude of this as VL and this as VC. So VC is less magnitude. So this implies VL greater than VC. Correct. So in that case, we have, in this case, the magnitude of VL is greater than VC. Therefore, we can rewrite this now. So when you have the vector 2 in opposite direction, so again we have VL minus VC here. So the phasor completes here and this is 5 and this is V. Correct. So this will be the final phasor diagram. So this is your VL minus VC. So from the above diagram, we observe that current lags the voltage by an angle phi. This one. Okay. So and you can write the impedance Z is equal to square root of R square plus XL minus XC whole square, because XL is greater than XC. So circuit is very similar to RL circuit because L is more here. So we can say it is very similar to RL circuit. Okay, and the power consumed here is again P is equal to VI cos phi, because we have studied in RL circuit, power consumed in the circuit or average power is VI cos phi. Let's take the next case, that is when case 2, when XL less than XC. When XL is less than XC, that means we have VL less than VC. So VL less than VC, we can write this waveform now, the phasor diagram, not the waveform, phasor diagram. If I is here, VL is less than, so let me write VL is this and VC is now more. Correct. So if you rewrite, so this is VR. So if you rewrite this phasor, this is I, this is VR. Now VC is more, so this can be VC minus VL and this can be V. So looking at this phasor now, again, here the current is leading the voltage by an angle phi. Correct. So we can write now Z can be equal to square root of R square plus, since XC is more, so XC minus XL whole square. Okay. So circuit is very similar to RC. Okay. Very similar to RC circuit, and therefore the power consumed very similar to RC circuit means P is equal to VI cos phi in this case. Okay. This is about when the circuit having capacitance greater than the inductance. Now let us take the case now when XL is equal to XC. So when third case we have XL is equal to XC. So if you take this case, let me write the phasor diagram. This is your VR. So in this case, VL is equal to VC. So both the phasors now, so this is VC and this is VL, this is VR. So this gets cancelled. So it is very similar to now the pure R circuit. So very similar to pure R means the power consumed P is equal to 0. Sorry, P is equal to 0. Correct? No power consumed. So P is equal to VI cos phi. So cos phi is 0. Phi is 0. So cos phi is 1. So P is equal to VI. So it is not 0. P is equal to VI. Because if you apply P is equal to VI cos phi. So cos phi is 0. So cos 0 is equal to 1. So VI into cos 0 is equal to 1. So you get P is equal to AI. So this is about the RLC circuit having three different conditions when XL is greater than XC, XL is less than XC, and XL is equal to XC. So with this, let us conclude that when XL is greater than XC, so it behaves like a RL circuit, and when XC is greater than XL, it behaves like a RC circuit. So therefore, power consumed remains same in both the cases. So thank you for watching this video.